Hello guys, this is CodeNCode and this is video tutorial, or this is the video lecture for the problem for the algorithm that we are going to discuss, Ford-Fulkerson method for max flow. If you haven't watched the previous lecture, I highly advise you to go and watch the previous lecture from Advanced Graph Theory series or Graph Theory series part 2. So first of all, what is maximum flow, the problem that we are going to discuss? Because we are in this lecture we are going to see how Ford-Fulkerson algorithms allows us to calculate the maximum flow of a given network. But the question is, what is maximum flow? Again, this I have already explained in the previous lecture. Just for recap, so a maximum flow is flow of maximum possible value from source to destination or sink. So this is source, this is terminating point or sink. So this is the original network in which the capacities are written here as denominator, and numerator represents the flow. Initially the flow is 0, and now we can see the maximum flow is of value 10. From source we are able to send 10 units of data or gas or whatever it is from source to destination. So the maximum flow, the value of maximum flow here is 10. Now this is maximum flow, and the problem or the algorithm that we are going to discuss allows us to calculate maximum flow of a given graph or network. So before we study Ford-Fulkerson algorithm, first of all we need to have knowledge of certain terminologies like residual capacity, because these two things we are going to use. Using these two things we are going to calculate, and Ford-Fulkerson algorithm actually depends upon these two things. So first of all, residual capacity. So residual capacity of an edge is defined as the capacity minus flow. So as we already know, each edge has defined certain capacity with it. So if there is certain flow x along that edge and its capacity was c, so the residual capacity of that edge would be c minus x, basically the remaining capacity. Now the reverse edge residual capacity, for each edge we are going to assume there is a reverse edge, there is a reverse imaginary edge, and we also need to calculate the residual capacity of that reverse edge. So residual capacity of reverse edge is defined as the capacity of the reverse edge minus the flow in the reverse edge. Now for that we need to know what is the capacity of reverse edge, because reverse edge do not exist in the graph. Now you might think, okay, if there is an edge from A to B and also in the same graph there is an edge from B to A, is B to A reverse edge of A to B? The answer is no. The reverse edge that I'm talking here is imaginary. So if there is an edge from A to B, we will assume there is a reverse edge for this A to B edge, that will be from B to A. Now since there is also an edge in the original graph from B to A, so we will also assume a reverse edge for edge B to A, and that would be from A to B. So of course for each edge we will have a reverse edge. So the residual capacity of reverse edge is defined as the capacity minus the flow. Now since the reverse edge is actually imaginary, so what is the capacity of that edge? The answer is of course 0. You can consider these edges as pipes, so you can transfer some data, like you can transfer like gas, oil, water, anything from that pipe, right? But we are assuming that there is a reverse edge from A to S. That is of course imaginary, so it cannot have any capacity of its own. That is why the capacity of reverse edge, the imaginary reverse edge, is considered to be 0. Now if there is a flow from original edge A to B, then the reverse edge of it will have minus of x flow. Now if you calculate, now using these two knowledge, the capacity of reverse edge, the capacity of reverse edge and the flow of reverse edge, you can calculate its residual capacity. So we would need residual capacity of the original edges as well as reverse edges. So if I show you with an example, so if this was the original graph, then This represents the residual capacity of each edge, and this represents the reverse edge residual capacity. Now see, you can see since the capacity of this edge is 6 and the amount of flow, the capacity of this edge is 7 and the amount of flow through this edge is 6, so of course residual capacity is 7 minus 6, that is 1. But for the reverse edge that we are assuming, that is from A to S, since the capacity of this edge is 0, flow is 6 in the original edge, so flow in this edge would be minus 6, so 0 minus minus 6 is plus 6. Basically, if there is a flow in the original edge of X, then the residual capacity in the reverse edge would be X, right? So yeah, if there is an in the original edge, if the flow is X, then in the reverse edge the residual capacity would be X as well. So here the flow is 6, so the reverse edge has also capacity 6. Now here the flow is 6, sorry, here is 6, let's go with different value. Here it is 4 from C to T, so T to C would be 4 as well. This here represents the residual capacity. What is the residual capacity? What does the residual capacity of reverse edge actually represents? So see, it represents the reversal of your decision. Basically, you decided to send a flow of 6 from the edge from S to A. Now this represents you can send a reverse flow from A to S. That what it would do, it would remove or reduce the flow from from S to A. Now assume you are sending like 6 units of water or gas from S to A, and then you have a choice to reduce the amount that you are sending by up to 6. You can reduce by 1 or 2 or 3 or 4 or 5 or 6, right? And that is what this reverse edge represents. It represents that you can reduce the flow by this amount. You cannot reduce the flow by 7, of course, and that is why the capacity is not 7 here. The capacity completely depends upon the flow in the original, because how much you can reduce depends upon how much you are actually sending. If you are sending 100 amount of data, you cannot reduce 101 from it. So this directly depends upon the flow. That is why the value of reverse edge residual capacity is equal to the flow. So it represents amount of data or flow you can reduce, and this represents the amount of data or flow you can still send. See, the amount you are currently sending is 5 out of 5, so how much you can now extra send? The answer is 0, because you are using the complete capacity. So this represents how much data you can still send. This graph represents how much you can reduce your flow. So these are the two important concepts that we needed to know before starting with Ford-Fulkerson algorithm. Now the first step is very easy. Just initialize the flow of each edge to be 0, and that we have done here. For each edge we have initialized its capacity, its flow to be 0, and the respective capacity has been shown here by denominators. Now the second step is to find the augmenting path from S to T. Now the question arises, what is an augmenting path? Now when I started the max flow or flow network graph series, I told you that I'll be using cpalgorithm.com as reference. So the link of this article I'll be putting in the video, and here you can read all about augmenting path. If I explain you in my words, so augmenting path is simply a simple path from S source to terminating point using only the positive capacity. So we'll be using these two because these two represents the capacity. So from source there are many augmenting path from S to T currently. You can use this path because this uses these 3 edges and each edge is having a positive capacity. You can use this path. Again, all of the edges used from source to destination are having positive capacity. Each time we'll be either using edges from here or from here. You can also use you can also go like here and then here and then here and then here, but you might think, okay, there is no edge from A to D. Yes, in the residual graph there is no edge from A to D, but in the reverse residual graph there is an edge from A to D. But the problem here with this edge is that its capacity is 0, and we are in the augmenting path. When we are going to find an augmenting path, we will only consider the edges which are having positive capacity. This edge, even though I can use, but is not having positive capacity. That is why I cannot use this edge. So let's start with finding an augmenting path. So one of the possible augmenting path is this. Go from here and here and here. All of the edges used are having positive capacity in the residual graph. So I can use these 3 edges, or basically I can use this as augmenting path. So the found augmenting path is this. Now, as you can see, the minimum flow you can send through these edges is 5, because this is having capacity 7, this is having capacity 5, this is having capacity 8. So the minimum of all of these 3 is 5. So you can send 5 amount of anything from source to destination, 5 amount of flow from source to destination. And why is that so? Since the minimum edge defines your bottleneck capacity, so you cannot go above that. You can't send 6 amount of flow, because if you send 6 amount of flow, each edge must have at least capacity of 6. So we will go with the minimum. So minimum capacity among all of the edges on the current augmenting path is 5. So we can send 5 amount of data from source to destination, 5 amount of flow from source to destination using this augmenting path. So let's do that. So the capacity of all of these edges, the flow of all of these edges would increment by 5. So you see, it will become 5, 5 and 5. Now since these 3 edges have been updated, so they will also be updated in the residual and reverse residual graph. So now since you are sending 5 amount of data, initially the capacity was in the residual graph, the initial capacity was 5, so 7, so it would reduce by 5. It was having 5, so it would reduce by 5 as well. This was having 8, so it would reduce by 5 as well. So the new capacities of these edges would be 2, 0 and 3. Similarly, this would increase. Now this would increase by 5. All of the edges in the reverse residual graph would increase by 5. All of the edges which were used in the previous augmenting path, and these 3 edges were used, so the value of these 3 edges would increment by 5, while in the residual graph the value would decrease by 5. Why is that so? You can see from here, the current capacity is 7 and current flow is 5, so of course 7 minus 5 is 2. That is why we would reduce amount of 5 from all of the edges used in the augmenting path from the residual capacity graph, and we would increment the same edges in the reverse residual capacity graph. Now find another. Now Ford-Fulkerson method or algorithm stops at the point where there is no augmenting path. Now here you can see there is another augmenting path. In fact, there are more than one augmenting path at this point. So I can use this as the next augmenting path. I can use this as the next augmenting path, because all of the edges that I've shown you are having positive capacity. So let's find the next augmenting path, and the next augmenting path found is this. Now one more thing, you might find similarity between the example used here in the cpalgorithm.com and the example that I'm using. In fact, the example used here and on the cpalgorithm.com is exactly the same, and in fact I have also used the same diagram because I was using the same examples, because when I'm preparing the PPT or presentation, it takes a lot of time drawing all of the graphs and making these graphs and edges and their capacity and so on. It takes a lot of time, so I thought, why not just use the same example which is used here on cpalgorithm.com, because the example used is very good, because it represents the use of both the residual capacity graph and the reverse residual graph. So I thought, why not use that same example and save some time. So now the next found augmenting path is this, because we can use this path because all of the edges used here are having positive capacity. Now the minimum of all of these 4, 3, 3 and 5 is 3, so of course we will reduce 3 from all of these edges. First of all, capacity of each edge, flow of each edges from the in the original graph would increment by 3 because minimum of the edges, minimum capacity of all of the edges on the current augmenting path is 3. So the flow I can send through this path is 3. So I'll be sending 3 flow from this path. So each of the edge, flow of each edge would be incremented by 3. Here capacity would decrement by 3. Here capacity would increment by 3. Now let's the current flow through S is 5 and 3 8. So let's see we can find another augmenting path. So let's start from here. From here I can go here and then here and then here. So of course there is again an augmenting path. Let's see if there is another augmenting path. If you see from here you can go here, from here you can either go here, but the problem is this is having 0 capacity, which is non-positive. We can go here, but this is again not positive, and there is no path from here to here in the original graph, so we can't use this as well. But in the residual graph you can go in the, you can take this edge from the original graph, I mean in the residual capacity graph, and this edge, I mean this edge from the reverse residual capacity graph. So you can use this edge and this edge and then again this and this. So this is also a valid augmenting path, but for now we'll be going with this augmenting path, sorry, this and this. So the minimum capacity is 1 2 3 and 3. So the minimum capacity on the path from S to T in the current augmenting path is 1. So all of the edges on this path will be incremented, the flow of all of the edges on this path will be incremented by 1. In the residual capacity, all of the capacities of all of the edges, used edges, would decrement by 1. And of course in the reverse residual capacity, all of the capacity of all of the edges used in this augmenting path will be incremented by 1. So this would become 4 1 1 6. Similarly, we have reduced the capacity by 1 of all of the edges used. Here in the reverse residual graph, we have increased the capacity of all of the edges used in the previous augmenting path. Now, here's the task for you. Try to find a new augmenting path. As you can see, the current flow is of value 9. And we know for this graph, the maximum flow is of value 10, which means we are left with one more augmenting path at least. Now, the question is find an augmenting path. Let's see, I can't use this edge. Basically, of course, I can't use this edge because this is having value 0, and in the reverse residual graph there is no path from here to here. So of course I can't use this edge or this edge. I can use this edge, so I can go from S to A. From there I can't use this edge, and in the reverse, of course, there is a reverse edge, so you can't go from A to B. So there's no way you can go from A to B, neither using the residual graph or the reverse residual graph. From here to here there is an edge, but the capacity is 0, so you can't use this edge as well. From here to here you can't use this edge. In fact, you can't use this edge because this is having this is an edge from D to A, not from A to D, but in the reverse it is an edge from A to D, so I can use this edge. So from S to A using this edge, from A to D using this edge, from D to C I can use this edge. I can't use this edge because this is from C to D. So from D to C and C to D. So now I am using a reverse residual edge. I'm using an edge from reversed residual graph. So I'm using an edge from here. So what it would have effect on the capacities of this. So of course, since I'm using this, so capacity of this edge would decrease by 1. Why 1? Because the edges that I'm using 2 1 1 and 2. So sorry, 2 3 3 because of this. 2 3 1 and 2. The minimum of all of these is 1. So of course I can send 1 unit of flow extra from this path. So let's do that. Since this is used from the original residual graph, so this would decrease by 1. This would increment by 1 because I am sending a flow of value 1 from A to D, that is decreasing in the original graph by 1 because I'm using in the reverse. So in the reverse it would be, in the original it would decrease by 1 as well as in the original, I mean in the reverse. So this would decrease by 1 because I am using A to D, that means I am decreasing. So this would increase by 1, this would decrease by 1, this would increase by 1, and this would increase by 1. So now, as you can see, this is the maximum flow you can achieve. Now try to find another augmenting path. There is And the answer is no. There doesn't exist any another augmenting path using either this or this graph. So this is where we stop, and the maximum flow achieved is of value 10. So this is how Ford-Fulkerson algorithm works. You start with the original graph, initializing the capacity, the flow of each edge to be 0. Then we keep on finding augmenting path and then keep on incrementing the flow through S. At the point where we do not find any augmenting path is the point where we stop, and that is the maximum flow achieved. Here we cannot find any other augmenting path, and hence we are stopping here. And this represents the maximum flow of value 10. Now the problem with Ford-Fulkerson algorithm, as stated by cpalgorithms.com, is that first of all, its runtime depends upon the flow. The runtime of Ford-Fulkerson algorithm is E times F, where E is the edge set and F represents the maximum flow. So of course the maximum flow depends, the complexity of the algorithm depends upon the flow, which is not good. So of course we will be using Edmond-Karp to implement this algorithm, which have a running time of VE square. As you can see, the running time of this Edmond-Karp algorithm does not depend upon the maximum flow. Now the second problem with the Ford-Fulkerson algorithm is that it does not specify in any manner how to find the augmenting path. It only tells you that okay, keep on finding the augmenting path till you can, but the problem is it does not specify any method to find the augmenting path, while Edmond-Karp algorithm uses either BFS or DFS, depends upon you. So we'll be using BFS. Edmond-Karp uses DFS. Oh, of course, since we are using graph and that can contain cycles, so we'll be using BFS. So it uses BFS to find the augmenting path. So these were the two problems with Ford-Fulkerson algorithm, which are overcome by Edmond-Karp algorithm. So in the next lecture we'll be studying Edmond-Karp algorithm. We'll be also implementing that algorithm. In the next lecture of that we'll be solving a problem. Then after that maybe I'll be making a lecture for Dinix algorithm. There's one more algorithm to find max flow. Let me just check. Max flow. Just a second. Flow. Yeah, there is also a Dinix algorithm which I think is having better running time than the Edmond-Karp algorithm. So we'll be also studying this. So this was all for this lecture. Thank you guys for watching. If you have any doubt or query or suggestion, you can post it down in the comment section. So thank you guys for watching. Until the next video drops, keep coding. Thank you.